Welcome to sitza.com. Here in this video we will learn about the dipole moment. We know a covalent bond is formed by the sharing of electrons, and an ionic bond is formed by the transfer of electron from the atom A to atom B. In a covalent bond, like suppose we can take an example of the hydrochloric acid, HCl. We know that there is a covalent bond and electron pair is being shared by the chlorine and the hydrogen atom, because chlorine has 7 electrons in its valence shell and hydrogen has got 1, so they will share the 1 electron there. Now this electron pair in HCl molecule is not right at the center. Rather, what we find in HCl molecule, the electron pair is slightly more closer to the chlorine because of its more electronegativity, right? So this electron pair will be slightly shifted towards the chlorine, and due to which it gets some negative charge and the hydrogen gets a positive charge. Now what we see, we find that a molecule has a positive end and a negative end. So this is what we call as a dipole, right? A molecule that has a positive and a negative ends, that has a dipole. So we say the molecule is polar. Okay, the molecule is polar, and the dipole we represent like this by an arrow, and it is pointing from positive end to the negative end of the molecule. So what is dipole and how we define actually the dipole moment? Dipole moment, you can say it is the product of the charge separation. How much charge separation is there due to the difference in electronegativity, right? So if the charge separation is more, you can say the dipole moment will be more. So basically, dipole moment is the product of the magnitude of the charge separation times the distance, right? The internuclear distance between the two atoms. So you can say here, this is the dipole moment, which will be equal to the charge separation. How much is the charge separation? Times the internuclear distance, right? The distance between the two centers, the positive and the negative end. That means actually it's the bond length, right? This is the bond length, and we measure this dipole moment in dBys, right? How much is 1 dBy? 1 dBy is 10 to the power minus 18 ESU, electrostatic units, centimeter. This is the unit of the dipole moment, because it is the product of the charge, right, and the distance here. So you can take the charge in ESU, electrostatic units, and the distance in centimeters. And 1 dBy is 1 into 10 power minus 18 ESU centimeter. HCl molecule, we find its dipole moment is 1.03 dBys, right? This is the dipole moment here. That means this is the product of the charge here times the internuclear distance. And this dipole moment is a vector quantity, means it has the magnitude as well as a direction there, correct? And this is the magnitude, and direction here you can say it will be from hydrogen to the chlorine. Different molecules will have different dipole moments. If you look, if you take here an example of the HF, right? HF molecule. Here we know that fluorine being more electronegative atom than HCl. Okay, chlorine is also electronegative atom, but fluorine is more. So that means in the HF molecule, the polarity will be more. It can pull the electrons more strongly. So that's why the dipole moment of HF is more than HCl. Right? Here in the HCl, how much is the dipole moment? It is 1.03 dBys. In HF, HF we find it is about 1.73 dBys, right? So it's more than HCl. Why? Why is it more? It's because that the quantity of the charge is more, right? So charge separation is more. Same will be the case with the HBr. Here the electronegativity difference is less, right? It can pull the electrons, but the charge separation will be lesser. And in HBr we find the dipole moment is about 0.73 dBs. For a polyatomic molecule, the net dipole moment is equal to the resultant of the dipole moments of all the individual bonds. That means if you have a molecule like this, it has two bonds there in the water, and oxygen being more electronegative atom, it will pull the electrons and hydrogen gets a positive charge, right? So this is the one dipole here, this is another dipole. The net dipole will be, the resultant will be in this direction, right? Okay, so this will be the resultant, or you can say the net dipole moment of the water molecule. And if you take the carbon dioxide, see the carbon dioxide here, oxygen being more electronegative atom, but we know that the bond angle here is 180 degree in carbon dioxide. The two bond moments here, they are in opposite direction and they will cancel out each other. So therefore the net dipole here will be 0. Okay, the net dipole in the carbon dioxide is 0. No doubt it has two polar bonds, but the net dipole is 0 because the two dipoles are in opposite direction and they cancel out each other, right? Because we have learned that the dipole moment is a vector quantity. It has a direction and a magnitude, and here the magnitude is same and direction opposite, so they will cancel out. The net effective will be the 0 here. Boron is less electronegative atom than fluorine, so you can say here in the BF3 molecule you have 3 bond moments, right? And here will be another one. Fluorine being more electronegative atom, that gets a negative charge, okay, and the boron will be positively charged. But if you look at these two factors here, this bond and this bond, the resultant of the two will be in between, right? This one, you can say this is the resultant, okay, this is the resultant of these two vectors. The resultant of these two vectors will be cancelled by this one, right? That means if you look at this bond moment here, it will be cancelled by the resultant of these two. Same thing will happen over here. If you look at these two vectors, the resultant of these two is in this direction, and that is being cancelled by this one, okay, and here are the two vectors, the resultant is in between, and that will be cancelled by this one. So actually you will see the net dipole moment in the BF3 molecule will be 0 here, okay. The net dipole here is 0. Now let's take another example of the CCl4 molecule, carbon tetrachloride. Here is the carbon in the center, and we got the chlorine atoms here, okay, chlorine atoms here, 4 chlorine atoms. Chlorine being more electronegative atom, it will pull the electrons towards itself, right? So this will be the direction of a dipole here. Another one here towards the chlorine, more electronegative atom. This is another vector. Now look at this one. The resultant of these three here, this one and this one, okay, it will be in between, which is actually being cancelled by this one, correct? So same thing, the resultant of these three, this chlorine, this one and this one, it will be somewhere here, which is being, this is the resultant of the three here, these three vectors, and that will be cancelled by this one, okay. Similarly, the resultant of this chlorine, this one, that will be in this direction, and that's being cancelled by this bond, right? This carbon chlorine dipole. So that means in the CCl4 again the net dipole is 0. The net dipole here is 0. In ammonia molecule, we know that nitrogen being more electronegative atom, it will pull the electrons, right? Like this. So it gets some small negative charge, and hydrogen the positive, right? And the direction will be like this. towards the nitrogen. It's a pyramidal shape. We have discussed it. The resultant of these three vectors will be in this direction, right? So it's not the zero dipole. It has some dipole moment here in the ammonia, and the dipole moment, in ammonia we find it is about 1.47 dBars. Hope you got the concept. Thanks for watching the video. Bye for now.